Welcome, everyone, to our Building the Future Women in STEM virtual family STEAM night, hosted by Scientific Adventures for Girls in partnership with Stanford University and Sandia National Laboratories. My name is Mariana, and I am the Family Engagement Specialist and Head Teacher for Scientific Adventures for Girls. Scientific Adventures for Girls is a nonprofit that provides after-school programs to TK through 6th grade children in the East Bay to increase positive attitudes towards science, technology, engineering, and math, which is STEM, and increase hands-on learning opportunities and encourage lifelong learning of STEM subjects.
Okay, and then hi everyone, my name is Angela Huang. I run the education and outreach programs at the Nano facilities at Stanford. So Nano is something that is really small, and we make these things in our labs that are used every day in our devices like microchips or sensors. And lots of technology that goes into bringing this event to life. You need your computer, you need your modem, you need your router, all sorts of things, right? And so that's what we do in our lab. So we're going to teach you a little bit about that. And so just to remember, nano is something that's really, really small, and it's 10 times 10 to the negative 9. Okay, thanks.
We're talking about super small stuff here. It's gonna get, woof, it's gonna blow your minds. So the theme for tonight's event is Building the Future. We will be celebrating women who work in the field of science, technology, and engineering and math, and learning from them as well. So let's start by thinking of our own futures. Does anyone know what they want to be when they grow up? What do you want to be when you're older in your future? Go ahead and put it in the chat. I'm very curious if we have people that already know what they want to be, or are hoping to, maybe if you have a job already, maybe you're thinking of a different
I see lots
job.
Marine biologist, a vet, a drummer, orthodontist, software designer, doctor, astronaut. Very cool.
Oh my goodness, I see a few different veterinarians. That's awesome. Architect, horse trainer, pediatrician. Oh my goodness, an astronaut, more vets, scientists. And someone said they don't know, and that's totally okay too, because you're still young and you can change your mind when you grow up and get to know about different careers. So we're going to be talking about some different careers in this webinar as well. A doctor, a teacher, and an artist.
A few bakers. I like that.
Police officer, FBI agent. Oh my goodness, there's some awesome jobs. So cool. All right. So yeah, keep adding them. I love to read these. But as a reminder, you can always use this chat function throughout the event. And you can chat to just us panelists or to everyone, which is panelists and attendees. If you have a question for one of our guests, you can use the Q&A feature. I see some questions already in there, and we'll do our best to answer those live and on screen. And as a reminder, for the best viewing experience, we recommend making sure that you're in gallery mode instead of speaker mode. And like I said, during this event, we'll be guiding the kids in the audience through a series of interactive science activities that showcase what some female scientists do for their jobs. We will also be asking the adults in the audience to participate in 3 different polls throughout the event. So please stick around and keep an ear out for your call to action when it's time to answer those questions.
Okay, so if you picked up your Family Science Night kit before tonight's event, go ahead and grab it. And it has all the materials that you should be able to, follow along at home tonight. But if you weren't able to pick up a kit, that's okay. You can still join us. And so you should have gotten a confirmation email that contains a list of materials that you can prep for, okay? So, and Mariana is gonna actually post the list in the chat now. And then we're going to use some of this time so you guys have a chance to, get ready and assemble the things that you need, or gather all the things that you need. Okay. And another thing is, if you can't do it with us this time, we are recording it and we will post it. So you can always come back to this recording. Okay.
Now, I would like to bring it over to Angela and Dr. Jessica Frick, who will introduce and explain our first live demo of the night.
So my name is Angela again. And so since, The theme is Women in STEM. We're going to share some of the awesome work that a few of our, women scientists are working on. So Jessica is actually at Stanford right now, and she's a postdoc in Debbie Sineski's lab, who studies graphene aerogels that are being sent to space. And these are some materials that can be really robust because they're really light, but also really strong. So we're going to actually give you a chance to see them under what's called an SEM. And these aerogels are so small that you can't actually see the little bubbles. They kind of actually look like sponges, but they're so small that you have to look at them under a microscope. And so we're going to use the SEM, which stands for Scanning Electron Microscope. So you can see those tiny air pockets, okay? And then again, so we're from Stanford, and then Jessica is part of Professor Debbie Sineski's lab, which is called X Lab, X meaning Extreme Environment Lab, and then Nano at Stanford, which is again the collection of facilities that we're a part of. So again, what is a scanning electron microscope? Why do we care about these things that are so small, and how do we see things that are so small? So this scanning electron microscope is a different type of microscope that produces images of a sample by scanning the surface with a really focused beam of electrons. So you can see, like, this is typically where you would have this is actually a piece of hair under a light microscope, right? But then here we actually have a piece of hair under a scanning electron microscope. So you can actually see the difference. This, you see the color and you generally see the structure, but here is actually where you see way more detail, which is really impressive. And then another cool thing is, SARS and COVID, that's part of the reason why we're on this call. One cool thing is that, the SEM, we were able to understand the way the virus works by imaging it under a microscope. So that's another interesting thing that happens, okay? One thing is, though, that these beautiful colors are actually just developed in the images. They're not actually on the, they actually are just black and white images, which I'll show you in a second. So why are we using electron microscope, right? We started with our eye, like for example, the hair. We can see our hair, but then we need to zoom in a little more. So we use a light microscope, right? And then to zoom in even more, we use an electron microscope, right? Because then you can see the actual individual cells and pieces of your hair. Okay. So a light microscope and electron microscope are very similar. You have a source and you have different types of special lenses, just like, sometimes maybe your friends or your family or yourself are even wearing glasses to manipulate the light to make it bigger. So we actually do that the same way, but with electrons. Okay, so I won't get into too much detail because I know we're kind of short on time. We care about the activity. So this is actually what you're going to look at. But I'm actually going to switch gears pretty soon and show you the SEM demo. So after this slide, I'm going to turn it over to Jessica to share her screen. So again, or Jessica, did you want to chime in here to talk about that graphene aerogel?
Yes, and
Okay.
I can turn my video on just for a second so I'm not a faceless voice. So hi guys. My name is Dr. Jessica Frick, and I'm in Debbie Sineski's X Lab. I'm trying to see my video, so, okay. Let me just turn this around real quick so you can see what we're doing. So I'm in this room right now. This is the instrument we'll be using. This was what it looks like on the outside. I'm sitting at the it, and now I will turn my video off. Okay, so that's where I am, and what we're going to be looking at today is a material called graphene aerogel, which is right there. So this is a very lightweight sponge-like material. So it's very lightweight, and you can see in that photo that it's resting on top of a flower. So it's very lightweight and so it has been used in studies to soak up different oils, and potentially it has applications in cleaning up pollutants from our oceans. And the image that you see on the right here is just an image from an academic paper where they actually took graphene aerogel and they soaked up oil, just like a sponge soaks up water. And the blue coloring is just effect. So if you go to the next slide, Angela, we're going to see how the graphene aerogel is sponge-like. So there's a Q-tip for scale there, so you can kind of see what the samples look like just by eye and the size of them. And on the left, I have a kitchen sponge. In the middle is just a general cleaning sponge. And then on the right is the graphene aerogel. So they could be similar, but under the microscope, I think you'll understand why they are sponge-like. So I'm gonna share the screen now. And we're gonna take a closer look. All right, so you guys see all this?
Yes.
All right, cool. So I showed you the instrument from the outside. Inside, this is what those samples look like. So you saw photos of the kitchen sponge, the cleaning sponge, and the graphene aerogel. And so here they are just sitting in there. And now we're going to, let's see, let me change the view. We're going to take a look at them under the microscope. So we will start with, I guess, the kitchen sponge. So you can kind of see this is also an optical view of the inside, and you just saw the stage move. So now we can turn on the electron beam. And let me zoom out a bit. So this is what that kitchen sponge looks like under the microscope. And you can see that there's all the fiber around it. I think it's just like a cellulose sponge. And you can see the pores here. Let me actually do a single quad mode. Get that to focus a bit more. There we go. Oh, beautiful. Okay.
We had someone ask if those are fibers.
Yes. So this is a standard kitchen sponge. And so this is just the cellulose fibers that make up this structure here. And you see that within the fibers, there's these holes that occur, and that's what allows you to soak up the water. It's these pores, we call them, that hold the water. And so it looks really cool under this microscope. And we can even, back in there, we can, let me get this out of the way, actively measure the pore size here. So we can see the pores are about 100 by 100 microns. Some of these are oblong, some of these are massive, about 200 by 200 micron. So this, let's get rid of those. Any questions before we move on to the cleaning sponge?
Someone asked, why are there holes?
So it is, there are, okay, that's an interesting question. This is just the, I guess, the manufacturing process of making these sponges. It just, how they're put together, it's just the holes are a result of that process. Okay, so now we can move on to a general purpose cleaning sponge. And you can already see, looking at the Electron image, that this looks very different. This is so cool looking. We see here that, again, it's a network of holes in this fiber, but the differences you can kind of see is the amount of that fiber to pore ratio. In the kitchen sponge, it was the ratio of the fiber to the pores was quite high, whereas there are way more pores to the fiber surface here. And these pores are very structured here. Wow. They're quite big, but there's a lot more of them. And this allows them to soak up more water than the other sponge we were looking at. Are there any questions here?
Not about this sponge, but someone asked about the aerogel, if it's been used to clean up the oil spill in Richmond.
I don't think it's been used in any real world applications yet. I think it's more of a, it's in its still research stages, but it has a potential to eventually be, used for that application once it's a more mature technology.
And also, why is it gray?
Oh, so this is, I guess, Angela, if you can answer this better, but this is just how the image looks like under the electron microscope. You do not see colors. And I guess, Angela, do you want to take this?
Sure. So basically what happens is it's really, this image is built from or created from electrons bouncing back to a detector. So it's just seeing intensity instead of colors, because we can't actually see electrons with our eyes, so we can't actually interpret color. So when something is black, it just means the electron went all the way through, and so you can't see anything. There's nothing bouncing back. So whatever material is there is really reflecting the electron, what you would call electron, quote unquote, lights. So you can actually see all the different dimensions and sizes. I hope that answers your question.
Yeah. All right, so I have no idea where I am with time, by the way, so if you guys need me to hurry up, just tell me. Otherwise, we can move on to the graphene aerogel sample. So now we've looked at, okay, the kitchen sponge, the multi-purpose sponge, and you saw how they both have pores. And now we can move on to the graphene aerogel.
Okay, so actually somebody asked a good question, which is why are some of the parts glowing? While Jessica is navigating, I'm going to answer it, is that because this is using electrons to bombard the material, it's actually doing this thing called charging. And charging means it's just an accumulation of electrons. Just like, you know, if you rub your head on a balloon and then the balloon sticks to your head, that means you actually charge the balloon with a static electricity. And this is actually a very similar thing where there's just too many electrons, so it kind of gets glowy, which is kind of cool.
Oh yeah, that's a good way to put it.
Anyway, go ahead.
So yeah, so as you're answering that question, we moved it over to the graphene aerogel, and you can see the structure under this microscope we reveal is much like both of the sponges, in that there is just a network of these pores that can be used to soak up things like water or oil. Yeah, we can maybe get a little closer and measure the size. So the pores for the kitchen sponge and the multi-purpose sponge, they are ranging from about 100 to 200 microns, I guess, in diameter. Let me get this a little more focused before we measure anything.
Yeah, and everyone is putting really cool comments, like it looks like a plant, it looks like lava bones, it looks like rocks. And I think that's actually a really good thing to take away, is that nature makes things very similarly, right? Like the inside of your bones is very similar structure where it's very webbed, but the material is different, right? The bone is really hard. Whereas a plant, it also is pretty hard, right? Where it's trying to build the plants of this size. So I think those are really good points. Cheryl asked a good question. What is the aerogel used for? So in this particular case, Jessica's working on this material so that they can send it into space, because it's not only really light, it's also very strong. So it can protect things, like, for example, the outside of the spaceship, and things like that.
It's also a very good thermal insulator. So you can imagine making, and it's very conductive too, because we don't really have time to get into this, but I guess the fiber structure in this sponge is made of graphene. And if you've ever, you've probably heard of the word graphene, it's kicked around a lot. It's a highly electrically conductive material. And so this is both, this material is both thermally insulating and electrically conductive, which is an interesting combination and can be used, I guess, in devices where you would need such properties. So yeah, any other questions? It just looks so cool. I can just like stare at this all day.
I think that's all the time that we have for now, but if you do have questions, if anyone in the audience has questions, maybe they can you can put them in the Q&A, and Jessica, you can answer them in the Q&A there. So yeah, use that Q&A function. And thank you so much, Jessica. That was so cool to see.
Yes,
and
let me
learn.
Stop sharing quick. There's a lot of windows open. There we go.
Okay, and I'm gonna start sharing my screen. Jessica is actually kind of doing a double whammy. She is also gonna do the Geodesic Domes activity, and so I'm gonna share the video that she did. So you guys need to get your materials ready. So this will be the steam kit, right? And so it's for Geodesic Dome, and so you're gonna need 25 toothpicks, 11 spice drops, and maybe a plate or a napkin to build it on, so you're not, directly building on a table. And then we're going to do this activity by playing the video. So when you guys are ready, we're gonna get started, okay? So I'll give you guys like a minute or two, yeah? Does that sound good? Oh, Leah's ready. Is everybody ready? Okay, I think enough people are ready that we're gonna start the video, okay? All right, so I'm gonna play.
Welcome to the moon, the Artemis project, landing the first woman on the moon in 2024. One of the goals of the Artemis project is to create a moon city. This will provide a space outpost for eventual exploration of asteroids or Mars. It will allow us to explore the moon and understand its geological history. And it will allow us to test for the sustainability of life. Can humans survive and thrive on bodies outside of Earth's atmosphere, like the moon and Mars? In order to create a moon city, the astronauts must construct buildings to live and work in. And that's where geodesic domes come in. They are durable and easy to construct. what is a geodesic dome? They are structures composed of triangular elements. Triangles are the strongest shape. That is because when a force, or load, is applied to one of the corners of a triangle, it is distributed down each side. The two sides of the triangle are squeezed, or compressed, and the third side of the triangle is stretched sideways, where tension occurs. In this activity, you're going to build your own geodesic dome using toothpicks and spice drops. To make the geodesic dome, you'll need 25 toothpicks and 11 spice drops. Step 1. Form the base. 5 toothpicks, 5 spice drops. To start, you're going to take your toothpicks and lay them out on your workspace in the shape of a pentagon. A pentagon is just a polygon with 5 equal sides and 5 equal interior angles. So here we have a pentagon. Once you have this laid out, you can take 5 of your spice drops. You're going to connect the entire pentagon. And here we have our finalized pentagon base. Step 2. Form 5 triangles using pentagon base with 10 toothpicks and 5 spice drops. To create your triangles, you first take 2 toothpicks and you're going to want to insert them into the base of your structure at an angle, because you'll be forming a triangle with the toothpicks, where they will reach at the ends, like so. Now to finalize the triangle, you will have to connect these toothpicks with another spice drop. So you can kind of see coming at an angle is the best way to do it for each. And there you have first triangle. And you can continue with your 8 remaining toothpicks and form triangles throughout the rest of your base. And there you have your 5 vertical triangles from your base. Step 3. Connecting the triangles to form a second pentagon using 5 toothpicks. You'll notice that the toothpicks are a bit long, so when you're connecting them, you're going to have to push really hard until they're almost all the way through, where your finger is being almost pricked on the other end of the spice drop by the toothpick. And here we have the first connection. And now you can take the remaining 4 toothpicks and connect the remaining spice drops around the whole second pentagon. And here we have our second pentagon, and you can see all the way around the tops of the triangles are connected. And now for our final step, step 4, cap the dome using 5 toothpicks and 1 spice drop. To start, you're going to need to angle your toothpick again so that one end can be directed all the way through the spice drop, all the way so that your finger is pricked on the other end again, so that the free end is pointing towards the center. So when you take another toothpick, you're going to be able to press that in and have the 2 ends point towards the center of the pentagon, as so. And you can continue doing this process throughout the rest of the spice drops. And here we have our finished geodesic dome.
Okay, everyone, thank you. How did it go? Good, bad, maybe? You guys can put it into your chats, or tell us what you thought of the activity in the chat box. Very good. Oh no. Okay, well, you guys can send us pictures too. You can put them on Twitter or Instagram. I'm trying to pull up the our Instagram, which is Scientific Adventures for Girls, all one word. Okay. Yeah. Or Twitter. And I'm going to put it in the chat, so you guys should tag us. And I'm actually going to hand it over. But actually, can we do a big double applause for Jessica? I think she did a great job, so we should be really grateful for Dr. Jessica. But I'm going to hand it over to Mariana, okay? Back to Mariana.
Yes, thank you, Angela. Now I'd like to introduce our next guest. Her name is Nora. She's an environmental technical professional from Sandia National Laboratories, and she'll be in our next video showing us a really neat demonstration of how watersheds work.
Hi everybody, my name is Nora. I'm from Sandia National Laboratories, and I'm going to talk to you today about watersheds. Right here we've got a model of a fake watershed. It looks kind of like a town or a city. We can pretend it's our city. Over here we've got houses. This is where we live. This is our neighborhood right here with some grass and some roads and some trees and my dog in the backyard. We've got a mountain right here with trees, and we've got some wildlife. Here's a birdie, tweet tweet, and we've got a little rabbit right there. We've got a parking lot over here where maybe our school is, or maybe our library is, and the cars park here and the cars drive on the road here. We've got, I'm calling this our dog park right here, because this is where the dogs like to hang out. Look at that one. And they like to roll around in the dirt, and they like to roll around in the grass, and it's really fun for them. We also have part of our watershed are these rivers. You can see the rivers coming through here, and then our lake. And underneath our watershed is what we call our groundwater supply. And right now there's no water down there, but we're gonna put water down there. So a watershed is where we get all of our drinking water. When the rain hits the earth, it's either going to soak into the ground, or it's going to roll off the top of these hills and then down into the rivers and then the lakes. And then we take water from the lakes and from the rivers or from the ground, and then we send it to the water treatment plant, which is this right here. And this is our water treatment plant worker right here. And they clean it and get it ready for us to drink. And then it gets pumped to our houses and to our schools and to our drinking fountains. So I want to talk today about different ways that we affect the watershed and different things that we can do to help keep it clean and safe. So let's talk about our neighborhood first. Sometimes when I'm in my backyard, I really want to have like just grass and flowers, and I don't want to have weeds or anything. So sometimes people use weed killer in their yards. I'm going to sprinkle some right here. It's bright pink, so you'll be able to see it. They sprinkle it in their yards in order to keep away all those weeds. All right. And then maybe over here at our school, they want to have the playground at the school really nice, so they put some weed killer there too. Definitely at our dog park, they want to keep it really nice so there's nothing pokey for the dogs and for the people. So this is a pesticide. And if you can imagine what's going to happen when it rains on our land, what's going to happen, that pesticide is either going to soak into the ground, or it's going to roll off the hills and into the rivers and onto the lakes. Okay? All right. The next part of pollution that we're going to talk about dirt. We're going to talk about soil. So soil is a tough one to think about as pollution because it's a natural part of our earth. When it's in the ground, it's actually really helpful. It can help, it helps move that water down through the earth and into our underground, our groundwater. So this dirt, I've got this spot over here at this house where I've actually never planted anything. It's just bare dirt. So I've got a lot of dirt on the surface. And dirt on the surface can cause a big problem because if it gets into our water and makes it muddy, it can be a big problem for the fish and the things that live in the water. We've got plants that live in the water, and the fish eat the plants, and then the ducks sometimes eat the fish and the plants. So everybody relies on this water being clear and not full of dirt. So another way we can create dirt pollution is with cars. Sometimes you've ever seen a big cloud of dirt behind a car. If you drive fast on a dirt road, you can really stir up all that dirt, and that can be pollutant. Or these dogs over here at our dog park, they might be rolling around in that dirt and create all kinds of dirt pollution there. Okay, since we're talking about dog parks, let's talk about this one. It's a funny one. When I take my dogs to the dog parks, I always make sure to bring my dog bag. It's for the dog poops, okay? When the dogs are at the dog park and they go to the bathroom, they are gonna leave, and if you don't pick it up, they're gonna leave their little poops all over the place. And those are not a natural part of our ecosystem. Like this rabbit who lives in the woods, his poops are fine because they're always there, right? But the dogs, we have a lot of dogs in this neighborhood, and they create a lot of poop. That's Peanut. That's Peanut. So over here in our neighborhood, by my house, where Peanut goes potty, we create a lot of little dog poops, okay? And imagine again, if it's gonna rain, what is gonna happen to all those chemicals inside that dog poop? It's gonna get washed down into our rivers and into our lakes. And then eventually it has to be, it's part of our drinking water, so it has to go to the water treatment plant over here and be cleaned by the water treatment plant employee right here. Okay, now, another type of pollution we have, this is a fun one. This one we see all the time. This one that we're calling litter. We're calling this one trash. So sometimes when you're driving down the road and you see like a plastic bag or like a wrapper on the ground, sometimes there's an accidentally litter. Like I think people sometimes don't do it on purpose. It might blow out of the trash cans. It might blow out of the landfill. So this one is representing litter, and Peanut's really interested in this one because these are sprinkles. So sometimes we've got too many pieces of trash. Sometimes over by the school, you ever see litter on the playground? Sometimes, right? So Peanut, no. So imagine again all of those different pieces of litter, and it's gonna rain. What's gonna happen to that litter? It's going to flow down the stream. It's gonna get into our lake. It's gonna really bother this guy right here, this little ducky. It's probably gonna bother this fisherman too, because trash can be really hard on the fish that live there. And then guess what? At the water treatment plant, they're gonna have a tough time making that water nice and clean for us again, okay? Because it has to be pumped back to our house, and that's where we get our drinking water. Even if you drink bottled water from the store, it still comes from our watershed. All right, you guys, now time for the fun part. I'm gonna be the rainstorm. We are gonna spray this with water and hopefully not scare the dog. And we're gonna see what happens, okay? Think in your head about what you think might happen when this gets wet and it's gonna flow downhill. Okay, so maybe get a close up and we'll see. There we go. It's raining over here in our subdivision. It's raining on our trees. Peanut is not interested in this part. It's raining over here on our school parking lot. It's raining at our dog park. It's raining a lot, and you can see, do you see how it's flowing down that river? That's all those pesticides. Remember, the weed killer was pink, and you can see it. I also can see some litter in there, some of those sprinkles. I really want to get this area over here. We got a lot of stuff. Big rainstorm. The poor dog is getting rained on. My dog might have gotten rained on a little bit. Now you can see what has happened. Now that all of this has washed these pollutants away, it all has ended up at the lowest point. And can you see it in the groundwater underneath? You might not be able to. And that groundwater, the river water, and the lake water are all part of our drinking water. It has to go to the treatment plant first. So, a couple things we can do to help keep it safe. Number one, make sure you don't litter, and make sure that you maybe pick it up if you see it. Make sure you're recycling and maybe putting your food into organic compost. If you bring your doggy to the dog park, make sure to bring your bag to collect their poops in. That's really important. Instead of using weed killer, you could pull weeds with your hands. That's a good one too. Instead of driving in your car, you could walk down the street to someplace close by that's safe, that has a sidewalk, and you can always plant trees and plant plants. Those are really important to help keep the dirt in the ground because the roots spread out down there and they make sure to keep that in the dirt in the ground. That's a watershed, you guys. Thank you.
Awesome. Wow. Thank you, Nora. That was really interesting to see all of that water pollution and how it really just goes into our groundwater. It can affect so many different things. So thank you for sharing with that. Without further ado, I'd like to introduce you to Nalini, who is also from Sandia National Laboratories, who will be guiding us through teaching us how to make our Flubber soap. Nalini Menon is a materials scientist at Sandia National Labs, whose interests are mainly in the areas of polymers. Polymers are everyday materials that range from your plastic cup to the O-rings on the space shuttle and everything in between, including slime. She is excited to be here to share her experiences as a scientist and also participate in a fun activity with you. So let's see, Nalini, if you'd like to start sharing your screen and unmuting yourself.
Hi, everyone. I'm Nalini Menon. I'm from Sandia National Labs. So excited to be here and be able to see all the wonderful presentations and demos right, just before I came on. So really excited to be here, and I'm sure you're having a fun time too. So one of my big passions has been science. Science is awesome. Science is cool. It goes from really, really simple things in life, such as soap, to something as complicated as graphene that's going to take us into space. So you saw the whole, the whole breadth of it today. All right. So one of the big things, one of the big aspects of soap is, what it can do for us. You all have been part of the coronavirus pandemic, right? We've been in it together. You've heard parents and teachers tell you, make sure you wear a mask, stay 6 feet apart from each other, and wash your hands with soap, right? So that's something that you've seen a lot. One of the things that a niece of mine asked me was, how does soap work? How does soap help with getting rid of, the virus from our hands, right? So I'd like to share a small presentation to that effect. All right. So how soap works. And I don't want to forget mentioning that we are going to do some really, really fabulous, fantastic hands-on soap making today. Okay, so let's talk about how soap works. How old is soap? Soap is as old as, probably not as old as dirt, but as old as dirt itself. So soap, do you know that when soap was first created, the Egyptians actually used soap to pretty much as a finish on fabric. They did not know that the soap that they made could actually be used to wash their bodies and themselves with, or their clothes with. So they just used it as a finish on cotton fabric. And then I think ultimately they stumbled upon the fact that they can actually wash, be clean with it, right? So in order to understand how soap actually works, let's go to this exciting slide. This has to do with the pandemic. And I want to give a shout out to all the healthcare workers, people who are, putting their lives on the line, to keep us safe and sound. So let's see how we can do our part, right? So here's the coronavirus. What you see in front of you is a picture of the coronavirus. I hope you can see my pointer. You see that this is how it looks. You've seen this picture a lot. There is a—
Nalini, we can't see your screen. I don't think you clicked share screen.
Oh,
if you were showing us slides.
Okay. I'm sorry about that, guys. So let me just share my screen. All right. Okay, there you go. You didn't miss anything. You did not miss much because the first picture was all of someone washing their hands with soap. So here's the coronavirus that I was just starting to describe. It's got these spike proteins on it, right? And this is actually a fat-like layer, a fat-like molecule that is sticking out, right? So how does that matter to our soap? Now, our soap molecules have a hydrophilic head, that which bonds with water, and a hydrophobic tail, that which likes oil or fat and avoids water. Okay, so this structure is very important. you may have heard of the word surfactant. This is present in all shampoos, soaps, detergents that we use every day. So, and all of them are made up of these tiny molecules. So what happens is when such a molecule comes, a soap molecule comes in touch with, say, the virus on different substrates, what happens is it actually, the hydrophobic tail attacks the fat layer around the coronavirus and makes a breach in it. And this is the happy part. It actually is able to, basically kick those spike proteins out and completely, convert the vicious virus into something which is totally harmless to us, right? So that is why we've been told, wash your hands all the time, right? So I hope that helped understand that little piece on how soap works in relation to the virus and why we do what we do during this pandemic makes sense to you all. Now, here's the next one. The next screen basically talks to us about rheology. So, what I was planning to do was actually in our demo, in our activity today, we're going to take something that is as liquid as this, a liquid soap, and we are going to convert it into a solid, sort of like the blue ball that you see on your screen right now, right? So how are we going to do that? The liquid soap kind of resembles the yellow liquid that you see on the left-hand side. And the cornstarch that you're going to add as a filler to make the soap is the white powder that you see on the side, right? So we're going to take a really fluid material and add a dry powder and put the two together and form a hard material like this. So you all have played on beaches, right, with sand and water, and you can change the ratio of sand to water and make it a little different each time, isn't it? So that is sort of what we're going to do. But behind all this is the science of rheology. It's the study of flow. So you can convert something which has very low viscosity and convert it into something that does not flow like this, this mixture of a liquid and a solid. So I made this, this little soap here myself, and that is using this liquid soap, and we actually added some cornstarch. And that's exactly what we're going to do in a few minutes. Actually, we're going to get started right now because I don't want to talk anymore. If you have any questions, I'll be more than happy to answer them at the end of the talk. But I'll give you a minute to basically collect all the items that you have, right? You've been given a kit with cornstarch and the shampoo conditioner sachet and the olive oil bits and the soap dye powder. So collect all of them and let me know when you're ready. That's it. Okay. We're going to get started soon. And to help me with the demo today, I have my daughter, Ria. Ria, say hello. Hello. Okay. All right. So I hope you all are ready. I would collect the ingredients. What Ria has in front of her is a bowl, a simple glass bowl. And she's going to follow the directions. The first direction, and I suggest you go along with us. We're going to take the cornstarch and add 2 tablespoons of cornstarch into the glass bowl. 2 tablespoons of cornstarch into the glass bowl. So the whole point in adding cornstarch is basically to make it, it's a filler, right? So what it does is it basically helps absorb the liquid soap and hold it to itself, right? So we're now going to add 1 tablespoon of liquid soap. Perfect. We have just added 1 tablespoon of liquid soap. I hope you guys are following along. And then what you have to do, if you don't have liquid soap, I guess what you could do is you could, you've been provided shampoos. If reach for some shampoo that's in the bathroom nearby, or if you can reach for any form of liquid soap, soap, detergent, anything would work. Okay, just add some soap, and then so we are making soap. We are making soap with the cornstarch and the liquid soap that you've been given. Okay, so yeah, so take as much as 2 tablespoons of cornstarch and 1 tablespoon of liquid soap. That's a good starting point. Okay, now why don't you mix it, Ria? Mix it well with either a spoon or with your hands, with your fingers, doesn't matter. Ria is choosing to use a spoon. That's fine. I guess she doesn't want to get her hands messy, but you're perfectly fine mixing it. You want to mix it well until it's thoroughly wetted out. The cornstarch is completely wetted out by the liquid, okay? You're still going to end up with a dry powder. You're not going to get a liquid, a flowing liquid at this point. Remember, you've added very little liquid to double the quantity of starch, right? That's right. So 2 tablespoons of cornstarch and 1 tablespoon of liquid soap. So you mixed it all up. Ria, can you show them what you got? Okay, perfect. It's still a dry powder. Now you add the oil. I'm sure you were given a sachet, a packet with 1 teaspoon oil in it. And so we have our little oil container, and Ria is going to add 1 teaspoon of oil into that mixture. Go ahead and please do the same on your end. There you go, 1 teaspoon of oil. So you might ask, does soap contain oil naturally? Yes, it does. Soap is a mixture of fillers. It's a mixture of surfactants, which we talked about earlier. And there is a little bit of fat molecules or oil molecules in it, right? The oil is a binder. It keeps everything. It helps in the wetting, and it helps keep everything together. Go ahead and mix it, Ria. Oh, by the way, here's the fun and exciting part. Ria just reminded me that we need to add some color. It is pretty bland looking at this time, right? It's white, and it's a white sticky fluid at this time. But she's like, let's add some color. So we are going to add pink, and you can either add liquid food color, or you can add a solid dye powder that you may have gotten in your kit. So Ria is planning to use a solid dye powder. Go ahead and add. And how much of it to add? Just add, as much or as little as you like. I suggest that you don't exceed too much, because you get color all over yourself. So I suggest you add like maybe half a teaspoon of color. Okay. So Ria, can you show them what you have in your bowl at this time? So she has the cornstarch mixed with the liquid soap. She has the oil, and she has the color. And now she's going to mix. If you don't have any, colors, packets, that's quite fine. The soap is going to turn out perfectly fine. Don't worry about it, okay? The color was just to make it a fun activity. If you don't have the color to add, not a problem. Start mixing everything with your fingers. Ria, can you mix everything with your fingers so we can explain rheology to people who are watching? I hope you guys are following along. We're just like you need a dough, right? Just like you need dough for cookie dough. That's what you're doing. You're kneading a dry cornstarch powder with the liquid soap and color. And Ria is mixing it with her fingertips, and trying to get as much of the dry powder as she can picked up by the liquid soap and oil that we have in the formula, right? So what we're doing right now is we're basically following a soap formulation. You probably hear the word sometime in your science careers ahead, but what we're going to do is we're just putting together a formula, a recipe, if you will. And Ria was able to squeeze all of it into a hard ball. I'm not quite sure it's that hard, but she's definitely working her way into it. Just place it between the palms of your hand and massage it, knead it as much as you need to get all the ingredients in, just like you would do with Play-Doh, for instance, right? It's just like it should be of a Play-Doh consistency at this time. Beautiful. So what Ria has is something that has that's looking just like what she has in her hands. You know, it's sort of, Ria, can you press on it and tell me how it feels? Does it feel hard when you press on it?
Yes.
Yes. Okay. And then what happens when you don't press on it anymore? Do the finger marks, you know, the imprint that you left on the soap disappear over time? I see some of it slowly disappearing. It may not be that clear on the video, but you know, if you leave the soap alone for some time, what happens is the liquid part of it starts dominating and the soap actually starts flowing slowly. It's really amazing to watch how the balance between a solid powder and a liquid soap can be so different. You know, you can turn up you can end up with completely different types of soaps, if you will. Some tacky and sticky, some really dry and, you know, kind of cracked up, and some smooth and something in between. So what we have is a soap, you know, knead it a little bit more, Ria. And, you know, let's, I hope that the folks online are following us as we go along. And, you know, I hope you had a lot of fun. What we demonstrated here is how to make soap, how rheology works, right? The flow of liquid versus solid. And then we're going to finally test our soap. You know, just like without the test, a scientific experiment is never complete until you test your product, right? So we made a product, which is the soap. Ria is going to pinch a small piece of that soap. And I suggest you do that too, of the soap you made. Yeah. And then, you know, we have a tub of water ready here. She's going to wash her hands with soap. Let's see if the soap she put together works. Work it, Ria, work it. There you go. You should be able to see a lot of soap, a lot of bubbles, a lot of sliminess, you know, because we did add a lot of liquid soap in it, right? So Ria just made liquid, you know, the solid soap turn back to liquid, and she's going to wash her hands in the tub of water. So I suggest you save your soap in a very safe place, so your family members and yourself, you all can use it for the next couple of days. And I hope you had fun with this activity. So it's so glad to be here. I just want to thank everybody for participating, and just want to say, science is cool, science is awesome. Thank you.
Great. Thank you so much, Nalini. That was really great. I'm so glad that we got to have another hands-on activity for you all. Thank you everyone for staying up until the very end, even through all the hiccups. We really appreciate you being here. I'd like to thank our partners, Stanford and Sandia National Labs, for helping SAFG put on this event. Feel free to, again, check us out on social media, our Facebook, Instagram, and Twitter, and our website. We also have summer classes, summer camp classes, week-long classes that are open up to everyone, not just girls locally in California, but everyone across the states is welcome to sign up for these online classes. You can find out more on our website for our summer camps. So thank you again for joining. Thank you for sticking around, and we hope to see you at the next event. Bye, everybody.